Hello, I'm Craig DeLancey, professor of philosophy at the State University of New York at Oswego. And thank you for watching this presentation, which is on the idea of consciousness as sampling of an information-dense environment. So I'm going to pull up my PowerPoint slides here so I can share those with you. And we can go over the argument together. The argument I'm going to make today concerns or is in the context of an ongoing project where I've been arguing that phenomenal experiences appear mysterious to us because they are enormously complex information states or information events. And I call that the complexity of consciousness claim. So to give us a context today, I'm going to spend a little bit of time describing that. But my main task today is to talk about this idea that phenomenal experiences are enormously complex information states. And there's sort of two aspects to that. On the one hand, there's the perception of the environment, the information in a perceptual experience. And then there's also the sampling that goes on in consciousness. You probably are familiar with the workspace theory of consciousness. This is a theory I find compelling and think is likely true. Proposed by Bars first, I believe. And this is a theory that access consciousness, the consciousness that you and I can report upon, is a kind of sampling of our perceptual information and other kinds of information that our mind has. And so the access consciousness is the kind of workspace where this information can rise up, be shared with other functional aspects of the mind. And in that theory, then, consciousness is a kind of sampling. And why would, and there's also the question then, my claim is going to be that the sampling is very, very complex. So we have the joint question, why would phenomenal experiences, perceptual experiences, say, be high information states? And also then, why would this sample of them be? Why wouldn't it just be a trivially, low information sample that you just take of your perceptual experience? So both of those are sort of mysterious. Why would that be? And today I'm going to defend those claims or explain why that would be. And that's a sort of two-step explanation. One is I'll make an argument about how competition between organisms that have representational systems puts pressure on them to have ever more rich information collection from the environment and also sampling by consciousness so that they can make decisions. And that's occurring in the context of a world that is information dense. So there's sort of a functionally no limit on, practically, let's say, no limit on, or physically would be the best way to put it, physically no limit on the upper bound, let's say, of the possible information that might be useful. There are practical limitations, and the organism has to pay for that representation, and that's costly. But it's not the case that the environment has an upper bound, right? It's just so complex and then more complex. So I'll defend that today, and it might, hopefully it'll be useful to you in your own research in that it could give you a different way of thinking about consciousness and also representations of the environment. So again, the context here, you should be wary that you've been using this word complex a lot, and you're probably well aware that it gets used in many, many, many different ways. And so there's profound ambiguities here. But I'm using the term throughout this talk. Whenever I say complex, I am referring to descriptive complexity, also sometimes called Kolmogorov complexity. And this is meant to be a measure of how compactly we can describe something. Perhaps the most intuitive way to describe descriptive complexity is to say the descriptive complexity of a description D is the size of the shortest computer program that can print D. So that's a very nicely intuitive way of putting it. We don't need computers to be able to describe descriptive complexity, but we're all familiar with them. And so it's a nice way of putting it. And I think you're all familiar with running out of space on your hard drive because you have so many pictures or videos. And that's because you couldn't squeeze that information more. Now we're talking about descriptive complexity. Here's an intuitive way to think about it. Here's an example that many textbooks on descriptive complexity use. I don't know who first originated it, but it's a beautifully elegant example. My variation on it. Here I have two 200-bit strings. One of these I made up, and the other I created with flipping handfuls of coins over and over. Once I tell you that, everybody gets that I made up the first one, and the second one comes from the coin toss. But that's rather mysterious in a way, because they're both equally likely to occur in 200 coin tosses, according to classical statistics. What's going on here? Well, from the perspective of descriptive complexity, what's going on is, I'm an organism, I'm lazy, I don't want to spend too much time and energy. So if I could just take some shortcut, a simple algorithm that will allow me to produce a string, I'll use that. And that's what I did in the first case. I just wrote 0, 100 times. The second string was costly because I had to go through these coin tosses. In terms of descriptive complexity, what that means is that first string number 1 there, has very little information. It's not descriptively complex because a very short program, basically a program that says print 0, 1, 100 times, it's going to be able to produce it. The second string is complex because the program to print it is basically going to have to say print, quote, we're going to have to type out that string, close quote. So it can't be squeezed, it can't be compressed. And imagine if these strings were, say, 1,000,000 times longer. Well, the program to print the first string would still be very tiny. It would only be a few more bits long than the program to print string 1. It would just say print 0, 1, 100 million times. Pretty compact. The second string, if we had a string that was 200 million bits long, and each bit was randomly selected, we would need a program that was at least 200 million bits long, because it would just have to quote the whole string and have to say print and then have that whole string, right? So some information can be really squeezed. There's a pattern and we can squeeze it right down, and some cannot. Some useful terminology in facts about descriptive complexity. Descriptive complexity is objective. You might be thinking, hey, there's different computers or different computer programs, so there's going to be different measures. And that is true, but always within the bound of some finite limit. So if you pick some computer and some computer language, I pick a different computer language, there's going to be some finite bound where my measure of descriptive complexity and yours match. They're under that. The difference between them is within this finite bound. So it is an objective measure. Maximally complex descriptions are said to be incompressible. Also, we can call them Chaitin random. Gregory Chaitin described that form of randomness, and so to distinguish it from other notions of randomness, it's useful to call Chaitin randomness. And here's an interesting fact: most descriptions for any language, any recursive language, are Chaitin random, or very, very, very close to Chaitin random. Insignificantly different from Chaitin random, within a few bits, basically, of Chaitin random. That's a shocking fact. It means you go out and most of the numbers are random, Chaitin random. Any language, most of the sentences of English are Chaitin random, in the sense that you're not going to be able to squeeze them anymore. There's not going to be a pattern in them that allows you to squish them down very much, just a few bits on general. So we sort of obviously ignore that fact. We go around and look for patterns in the world, and we ignore the fact that most things don't, they don't have a compressible, simple pattern within them. What does this have to do with consciousness? Well, I want to ask you, think now. Look at this painting by Pollock. I believe this is Lucifer. Imagine with me for a moment, do a thought experiment. Imagine you have a friend. She's never seen, she's interested in painting, but she's never seen a modern art piece. She's never seen abstract expressionism. She's never seen a painting by Pollock. And you're going to talk to her on the telephone, and you're going to describe for her this painting well enough for her to recreate it. maybe not perfectly, but well enough to recreate it. So, glancing at it, I think it's Pollock's painting. Well, you and I both know this is a practically impossible undertaking. Why is that? Is that because Pollock's painting is immaterial, it's non-physical, it's emergent on, physical properties, but is not itself a physical property? No, none of these dualist reasons are needed for why our friend's not going to be able to recreate the painting. What's happening is that the painting has a tremendous amount of information in it, visual information in it. And our voice, a telephone line, that's a very low bandwidth channel. And she's on the other end hearing it. It's coming into her, the parts of her brain processing speech. And it's just, we're just not built to take all that information, visual information, turn it into oral information, transmit it over this little low bandwidth channel, pick it up, remember it all, and turn that into visual information. We can't do it. So it's the fact that this painting is so complex that makes it, in a way, resistant to that sort of description, right? And transmission and understanding. And my argument is that consciousness itself is like that in general, right? That phenomenal experiences are the ones that we think are mysterious. So we don't tend to think, doing a math problem is mysterious, but we tend to think visual experience or tasting a strawberry is mysterious. So I call that the paradigmatically mysterious phenomenal experiences. Those phenomenal experiences, my claim is, any phenomenal experience E is paradigmatically mysterious if and only if it has some property R that makes it, the kind of experience it is. So such that to explain that phenomenal experience, you're going to have to explain R. And R is very descriptively complex. So I'm not going to talk about it today, but if, I'll give some references at the end. If you look at the canonical arguments that consciousness is irreducible, that it's probably not physical, those arguments all look good if either A, consciousness is non-physical, or B, consciousness is so complex that we had this intuitive and grasp, but very solid understanding that you're not going to be able to explain it in these low bandwidth channels of speech and theory and so on. All right. That brings us though to this sort of back question, more fundamental question. Hey, DeLancey, you had this interesting hypothesis. You defended it in some papers claiming, that phenomenal experiences appear mysterious because they're descriptively complex. But why would they be descriptively complex? Why are these organisms going around with these representational engines that are, generating and storing these very complex representations of the world, and then at the layer of access consciousness, sampling and generating very complex samples of that they use to make behavioral decisions? Why would that happen? And there's two factors we need to explain this. The first is that there's going to be, in general, it's in balance with cost, but there's a fitness benefit driven by competition to high information representation. Again, within the bounds of the fact that it's costly to have representation. Brains are very costly, along with the digestive system, the most costly organ we have, right? So obviously, there's a balance between the fitness benefit and the cost, but they're holding the cost constant. There is an advantage driven by competition to higher information representations. And furthermore, we need to claim that the world itself is very complex. So I'm going to defend both those. First, useful when we think about this evolutionary story to think about competition. So I'm going to talk about camouflage and predation as an example, but we could think of any other kind of competition where representation plays a role in the competition and it would work. But let's think about predation and camouflage. There's this interesting idea that when animals first evolved in the Ediacaran era, this is before the Precambrian era, way back, right, that there were yet no aggressive predators. There were filter feeders, but that was it, right? And some paleobiologists have described this as an Eden, like a world before predation. And the animals were quite like plants, right? They were just sort of filter feeders. Most of them were sessile. And it's an interesting idea, right? And the fossil record seems to suggest it. But as you and I know, over millions of years, predators evolved. This is Amylocaris, right? They're thought to be one of the first large predators. It's got eyes. It's locomotive. It's got limbs to grasp prey, right? So now it's got a problem it's got to solve. It's got to locate, move towards, and, you know, attack, kill, consume prey. Eventually its prey is going to start moving away, and it's got to be better and better at this task. And in fact, one of the big issues is that you know, as this task progresses and the competition goes on over time, as you know, camouflage evolved is an interesting example. So, you know, that's just, again, one type of a competition that needs representation. But you think about camouflage, right? The prey organism has an advantage for better camouflage. So, you know, it's there's evolutionary pressure for the camouflage to improve. And the predatory organism has an advantage to being able to distinguish camouflage from the environment that it's, you know, that the organism is pretending to be part of, right? It's pretending to be a tree or whatever it's pretending to be. And so there's a cycle here where, you know, you can improve the camouflage, or you can improve the perceptual, the amount of perceptual information that's coming in, and also you can improve the sampling of that information so that you make better decisions. But then, you know, the response to that could be to improve camouflage. And as you and I know, that can become extraordinary, right? Organisms now have just very impressive camouflage, and you got to be sharp-eyed, as we would say, right? That is to say, you need to have very high information perception of the environment, and then high information sampling to drive behavior to go catch that octopus and eat it, right? So again, of course, there are costs of representation, very high costs. So it's not that, you know, you can have boundless increase in representation, but you know, within the bounds of that cost in this competitive environment, there's a benefit to more perceptual information being gathered, but more high information sampling of that perceptual information. Well, wait a minute, DeLancey. Couldn't it be that the world, though, is only so complex and not much more complex? And so, you know, once my representations are good enough, I can stop, right? I don't think so. I'm going to make this is my final claim today, and it's a metaphysical claim, and it might be of interest to you in your own research. Let me know if it is. But the claim is, I'm going to claim the world is information dense. Now, I'm coining this term information density, and the idea is that the information density of something is the amount of energy or matter required to describe it completely, relative to the amount of matter or energy that goes into the object, constitutes the object or event. So let me suppose you're sitting at a table. How well could you describe that table for me? How much matter and energy would it take to store that description? Of course, you can do a trivial description. You can tell me how tall, wide, deep it is, and, you know, I could recreate that table, but it would just, at best, I would have something with the same surface area as your table, right? It wouldn't be your table. So how much information would you have to give me for me to recreate an exact duplicate of that table? And if the amount of information is so great that the storage demands of that information approach the mass of the table itself, like the mass required to store that information approaches the mass of the table itself, now we're getting to we're approaching an information density of 1. By the way, if the world is information dense, footnote here, this is an argument against all the simulation arguments. You're probably familiar with this. Many arguments that say that we're living in a simulation. They all depend upon the implicit assumption that the world is not information dense, and so that you can have this computer sitting somewhere and it can simulate the entire universe. But if the universe is information dense, you're going to need as much matter as is in the universe, as much energy as is in the universe, at least to simulate it with accuracy. End of footnote. So I'm going to make the claim, again, definition though, an object would be maximally information dense if the information density is greater than or equal to 1, right? And I'm going to make the claim, I got a weak and a strong claim. Either is sufficient. The weak claim is that many objects or events are nearly maximally information dense, and the strong claim would be that all objects or events are maximally information dense. I think that might be true for metaphysical reasons, because my suspicion is that, well, wait a minute, if you needed less information to describe this absolutely without loss, this particular object, I'm not sure why it is the object it is. But anyways, I'm not defending that claim. I'm just saying that, between the weak and the strong claim, the weak claim is sufficient. Sufficient for what? Well, it's sufficient for us to say that there's really going to be no physical, I wrote here practical, but I should have said physical upper limit to the complexity of the information required to distinguish any two arbitrary structures. There are going to be practical limits for organisms in that there's a cost to representation, of course, right? But there's no sort of physical limit in the world, like, you've hit maximum information, things don't get more complex than this. You could have larger objects, right? For example. And that's going to mean there's no, and again, I should have said physical, there's going to be no physical upper limit to the potential for competition of a representational ability between organisms. The camouflage can keep getting better, and then the amount of information required to distinguish between the prey and the thing is trying to pretend it is tree or coral reef or whatever. The amount of information that you can use could grow indefinitely. Again, I shouldn't have said practical, because there are practical limits in that. Brains are costly, right? At some point, it wouldn't be worth it. But there's not going to be any physical limit to it. So we put this together, that the world is, let's say the weak information density claim and the recognition that competition between organisms that do have representational systems leads to benefits to ever more information in their perception and ever more information in their perception sampling. And we see there's no, in principle, limit to the amount of information that organisms could be gathering from the environment and could be sampling in their consciousness. And that's why, in fact, we should expect consciousness to be enormously information dense, enormously complex. And given that, it's going to appear mysterious to us. And so our question should be, gosh, maybe it's Occam's razor, maybe it's a simpler explanation that it's actually a physical phenomenon, but an enormously complex one, as opposed to our non-physical alternative theories. Although, of course, I recognize that's, Occam's razor isn't proof. It could be that dualism is true. I want to close with one warning here. You may be thinking, wait a minute, DeLancey, I got this friend, he's in the physics department. He's got this textbook. He tells me that, all the physical laws that we need are in this textbook. Isn't that textbook, all I need? Isn't the information in that textbook all the information? And from that textbook, I can derive everything I need. So in other words, isn't there an upper limit here? And the answer is no. And the reason is because of a theorem I call the complexity cost principle. It's just a theorem I came up with. It's just a variation of a common theorem in descriptive complexity. Here's the complexity cost principle theorem. If a description D is very much more complex than a theory T, then D cannot be identified as a consequence of T without the additional information, at least as great as the difference between the complexity of your theory and the description. So it's a no free lunch principle. You can prove this, pretty straightforwardly in logic. And what the theorem tells us is that, even if we had the complete physical theory, the arrangements of things in the world is itself a kind of complexity. And so you can't, to derive that complex physical phenomenon from your physical theory, you got to add to your physical theory information. And you're going to have to add as much information basically as is in the proper description of that phenomenon. So maybe physicalism is true and a compact physical theory is sufficient, and in the sense that physicists will probably mean it complete, but that doesn't mean that from it you can derive the complex phenomenon. No, you need extra information. And again, that's provable. So there shouldn't be any controversy about that. If you're interested, here are some references to papers in which I do defend the complexity of consciousness theory, right? The idea that this tells us why consciousness is mysterious. And I'll stop there. I want to, thanks for watching this video. I look forward to, doing this sort of strange COVID conference that we're all doing, and watching some of your videos. And hopefully we can all have some conversations. It's not like being there in Tucson, is it? But it's, next best thing, I guess. So thanks very much for your time. I really do appreciate it. I know you get a lot of other things to do. And please don't hesitate to write me. If you Google me, I'm the only Craig DeLancey. If you have any questions, and because I'd love to get feedback and see if my ideas are useful to anyone else, or if you think your ideas might be useful to me. Thank you.